They say history is written in stone, but some stones whisper secrets our textbooks can't explain. Across the ancient world, we find artifacts that should not exist, at least not without modern technology. Surfaces carved so smooth they reflect light like glass, joints aligned to within a fraction of a human hair, and metals infused with microscopic structures rivaling the precision of today's laboratories. It's as if the craftsmen of thousands of years ago were working atom by atom. And if that's true, it changes everything we think we know about the past. Perfection is a word we rarely use for anything made by human hands. Even in the modern age of laser cutters and computer-guided machining, tolerances have limits. We accept that nothing is ever flawless. Every edge has micro-imperfections. Every surface bears the signature of the tool that shaped it. Yet, scattered across the world's oldest monuments and artifacts, there are examples that seem to defy this rule entirely. Imagine a block of granite weighing several tons, quarried with Bronze Age tools. Yet its surface is so flat that when measured today with precision instruments, it deviates by less than a single millimeter across its entire length. Or an ancient gold ornament, hammered into a form so precise that under an electron microscope, its microscopic patterns display a uniformity that seems more like the product of atomic layer manufacturing than of human hands. How could this happen? To understand the scale of the mystery, you need to realize just how resistant these materials are to shaping. Granite, for example, ranks high on the Mohs hardness scale, far harder than the copper or bronze tools available to the civilizations that supposedly shaped them. Under normal conditions, even iron chisels would struggle to produce anything like the smooth, glass-like surfaces we find in certain temple walls in Egypt, Peru, and India. And yet, they exist. Mainstream archaeology often offers explanations that, at first glance, seem reasonable. Long, patient work by skilled craftsmen, sand abrasives, ingenious but simple tools. But when engineers, stonemasons, and materials scientists examine the evidence, many find themselves unconvinced. Take the perfect boreholes found in hard stone at sites like Abu Sir and Giza. Modern machinists who have studied these holes note spiral tool marks that would be incredibly difficult to reproduce today, marks that suggest drilling speeds and feed rates far beyond the capabilities of ancient hand tools. Some holes appear to have been cut through granite in a single, uninterrupted motion, without the chattering or uneven wear we'd expect. And then there's metallurgy. Damascus steel, famed for its strength and beauty, was once thought to be the pinnacle of medieval craftsmanship. But when researchers examined ancient Damascus blades under high-powered microscopes, they discovered something astonishing: nanowires and carbon nanotubes embedded in the metal structure. These are features we can replicate today only in controlled lab conditions, yet they appear in weapons forged over 1,000 years ago by smiths who supposedly had no knowledge of atomic theory. When you zoom in far enough, the picture gets even stranger. Some ancient alloys show grain structures and impurity distributions that are so uniform, it's as if the metal had been manipulated at the level of individual atoms. We don't find signs of repeated melting or hammering. We find evidence of processes we simply can't recreate without advanced metallurgy. This is where the mystery deepens. If these examples were rare outliers, they might be dismissed as flukes, the lucky results of unusual materials or accident. But we find them again and again across continents and cultures that, officially, had no contact with one another. The megaliths of Pumapunku in Bolivia, the ashlar masonry of Cusco, the precision-cut sandstone of Sacsayhuaman, all show similar hallmarks of engineering that seems to exceed the known technology of their time. And here's the most unsettling part. Some of these sites don't just show extraordinary precision, they also show evidence of techniques we don't understand. Stone fused as if by intense heat, surfaces polished without abrasive residue, joints so tight that even modern engineers have trouble replicating them without digital modeling. In some cases, blocks appear to have been shaped to interlock in complex three-dimensional patterns, fitting together like pieces of a jigsaw puzzle with no mortar. The ancient builders, it seems, were not merely skilled artisans. They were engineers working with an understanding of materials that feels eerily modern, or perhaps even beyond modern. If these feats were achieved without steel tools, without diamond-tipped saws, without modern forges and lathes, then what exactly was going on? Were these simply the extreme outliers of human craftsmanship, products of lifetimes spent perfecting a single skill, or do they hint at something else entirely, something we've lost? In the modern world, we have names for these levels of precision: micromachining, nanostructuring, atomic layer deposition. They require controlled environments, high-energy tools, and knowledge of materials science that took us centuries to develop. But if even a fraction of these ancient achievements were the result of comparable methods, then we are forced into a startling conclusion. Either our ancestors knew more than we think, or someone, or something, taught them. And that's where the trail of evidence begins to lead us, deeper into a past that doesn't fit neatly into our history books. A past where the limits of human capability might have been pushed to the very edge, or perhaps past the edge entirely. Next, we follow that trail to the first real case study, an ancient artifact whose microscopic secrets challenged the very idea of technological progress. In 1851, deep in the goldfields of South Africa, miners working the Transvaal region began pulling something strange from the earth. They were there for precious metal, gold, diamonds, platinum. But amid the raw ore, workers discovered small, perfectly formed metallic spheres. At first, these finds were nothing more than a curiosity. Dozens of them turned up, then hundreds. They were the size of a large marble, some a little smaller, and most had an uncanny feature: 3 perfectly parallel grooves running around their equator, like the lathe marks you'd see on a machine-turned ball bearing. To hold one of these spheres in your hand is to feel the weight of impossibility. The grooves are too precise, too uniform to be the product of natural erosion. Geologists were baffled. They didn't appear to be carved or hammered, but manufactured. Yet the spheres were found embedded in solid rock, in strata estimated to be over 2 billion years old. 2 billion years. That's older than complex life on Earth, older than animals, older than plants. Back then, the most advanced organisms were single-celled bacteria drifting in ancient oceans. And yet here was something that looked like the product of a machine shop, sitting inside rock that predated humanity by a geological eternity. Skeptics, of course, have tried to write them off. Some say they're concretions, natural mineral formations that just happen to look artificial. But there's a problem. Natural concretions don't form with perfect symmetry, nor do they cut parallel grooves into themselves. The level of geometric perfection in these spheres is something our own engineers would struggle to achieve without precision equipment. Tests revealed something even stranger. The spheres are made of a nickel-steel alloy that doesn't occur naturally in the region. Not just any nickel-steel, but an alloy so pure and so hard that it scores high on the Mohs scale, comparable to hardened steel. And remember, this was supposedly sitting in ancient rock, untouched by human hands for billions of years. If these objects were artificial, then we're forced into 2 equally impossible scenarios. The first, they were made by humans, or human-like beings, so far back in time that they've been erased from every scrap of the fossil record. This would require rewriting the entire timeline of our species and its ancestors. The second, they were made by something else entirely. When the Klerksdorp spheres, as they came to be called, finally drew wider attention in the late 20th century, they became a lightning rod for controversy. Museum curators refused to display them, calling them anomalies best left unexplained. Scientific journals largely ignored them. A few researchers examined them closely and admitted reluctantly that they didn't have a good explanation. And so they remain in that liminal category, too strange to dismiss, too dangerous to embrace. But this is only the beginning. Because the deeper you look into ancient anomalies, the more you realize that the Klerksdorp spheres are not alone. In Colombia, pre-Columbian gold artifacts have been found that look exactly like modern aircraft, complete with wings, tail fins, and vertical stabilizers. In India, 2,000-year-old surgical instruments match the design of modern stainless steel tools. In Japan, a stone compass rose has been discovered on a remote island, perfectly aligned to the cardinal directions with a precision that suggests advanced surveying techniques. And yet, each of these discoveries is usually explained away as coincidence, misinterpretation, or pure chance. But here's the thing about chance. When it happens once, you can dismiss it. When it happens twice, you can be skeptical. When it happens over and over again, across thousands of years and thousands of miles, you have to ask yourself, is it really chance? Or is it the shadow of something we've forgotten? In the case of the Klerksdorp spheres, the shadow is especially deep. Because if you accept that they were manufactured, you have to accept something else. They were made not just before history, but before the Earth as we know it. And that changes everything. In the next part, we'll travel from South Africa to the Egyptian desert to examine one of the most famous and most hotly debated examples of impossible precision in the ancient world. This one isn't the size of a marble, it's the size of a building, and its construction still defies us to this day. Shift your mind from a metallic sphere small enough to hold in your palm to a block of stone so massive that modern cranes would groan under its weight. In the heart of Egypt's desert plateau, far beyond the gaze of tourist crowds swarming the Great Pyramid, lies an unfinished dream in granite, the unfinished obelisk of Aswan. Had it been completed, it would have been the largest stone ever quarried by human hands, nearly 137 feet long, weighing an estimated 1,200 tons. That's the weight of 2 fully loaded Boeing 747s, carved from a single piece of granite. But here's the riddle. We don't just marvel at its size, we marvel at how granite is unforgiving. To shape it with our best modern tools, diamond-tipped saws, hydraulic drills, takes time, patience, and extraordinary precision. Yet here, in the bedrock of Aswan, we see cuts that are smooth, uniform, and eerily machine-like. We see scoop marks so consistent in depth and curvature that engineers have likened them to the passes of a high-powered rotary grinder. According to mainstream Egyptology, the work was done with pounding stones made of dolerite, a slightly harder rock. Workers, we are told, stood for hours upon hours, smashing the granite with handheld pounders until it flaked away. But if you've ever tried breaking granite with another rock, you know it's absurdly slow. Minutes to chip off a fragment, days to make an impression. And here in the Aswan quarry we see entire channels cut with fluid sweeps, almost as if a drill bit the size of a man was lowered and guided across the surface. Even more unsettling, these marks are identical to tool signatures found in other ancient sites around the world, separated by oceans and supposedly by thousands of years. Pumapunku in Bolivia, the megaliths of Baalbek in Lebanon. Different cultures, different continents, but the same style of deep parallel tool grooves, the same impossible precision. It forces a question that Egyptology tends to sidestep. Were the ancient Egyptians inheriting, rather than inventing, certain construction techniques? Did they at some point have access to methods or machines now completely erased from our historical record? And if the Aswan obelisk had been finished and moved, an engineering feat in itself, it would have stood taller than most buildings in Cairo today. Yet no evidence exists of the massive ramps, scaffolds, or infrastructure that would be necessary to move such an object. It's as though the tools and methods were lost overnight. Some researchers suggest this is exactly what happened, that a sudden catastrophe, whether natural or human-made, wiped out a prior chapter of civilization, a chapter that possessed knowledge far beyond what we attribute to the ancients. This isn't just idle speculation. Across Egyptian temples, we find hieroglyphs that seem to depict sophisticated devices. A light bulb in the Dendera temple, what looked like schematic diagrams in Abydos, and precise astronomical alignments that match the accuracy of today's observatories. Yet the obelisk remains frozen in time, half-carved, abandoned mid-process as if the workers simply vanished. It sits there under the blistering desert sun, like a paused frame in an ancient documentary we were never meant to see. And here's the truly strange thing. Modern experiments to replicate the Aswan cuts using dolerite pounders fail. They leave jagged, inconsistent impressions, nothing like the smooth, parallel grooves in the quarry, which leaves us with two uncomfortable options. Either our dating of the quarry is wrong and the marks were made much later with advanced tools, or, far more disturbingly, the marks were made much earlier by a technology we have completely lost. In either case, the official story doesn't hold. The unfinished obelisk isn't just a monument to ambition. It's a monument to an unsolved mystery, one that hints at a shared global knowledge long before our recorded history begins. But if we leave Egypt and cross the Mediterranean, we'll find ourselves in another ancient site, one even more baffling because it's hidden beneath the sea. There, massive stone blocks rest in perfect arrangement, swallowed by the ocean thousands of years ago, and their existence could rewrite the origins of civilization itself. Picture the scene. You're diving off the coast of Japan, the sunlight streaming down through crystal water, illuminating a rugged sea floor. Suddenly, the contours sharpen into clean lines, straight edges, right angles, terraces and stairways. It's as if an entire stone city is sleeping beneath the waves. This is Yonaguni, a submerged site off the southern tip of Japan's Ryukyu Islands. To the untrained eye, it might seem like an oddly symmetrical rock formation. But to divers and researchers who have explored it for decades, it's something far stranger, a geometric arrangement that defies the randomness of natural erosion. Massive platforms rise from the seabed like the stepped bases of ancient ziggurats. Long flat walkways stretch out before dropping into sheer vertical walls, some more than 30 feet high. Staircases with perfect risers, each step matching the next within a fraction of an inch, ascend to what looks like a ceremonial platform. Rectangular pools and a perfectly flat plaza sit above them, eerily similar to the urban layouts of ancient cities. Mainstream geologists argue that the site is natural, the product of sandstone fracturing along horizontal and vertical joints, then eroding over time into clean angles. But this explanation runs into a problem. The patterns here aren't just geometric, they're architectural. Right-angled corners connect with terraces at exact 90-degree turns. Massive blocks appear intentionally isolated from the bedrock as if quarried. Certain corridors seem aligned with astronomical points, just as we see in megalithic sites above sea level. Marine geologist Masaki Kimura, who has spent years studying Yonaguni, believes it's at least 10,000 years old, placing it well before the dawn of known Japanese civilization. If he's right, it predates the Egyptian pyramids by thousands of years and would have been constructed at a time when human societies were supposedly still small, scattered and primitive. But here's where it gets even more intriguing. At the end of the last ice age, roughly 12,000 years ago, sea levels were more than 300 feet lower than today. Vast stretches of what is now seabed were dry land, fertile ground for settlements. As the ice sheets melted and oceans rose, entire coastal civilizations could have been swallowed, leaving only the highest structures visible today to divers like ghostly reminders of the past. This drowned civilization theory isn't unique to Yonaguni. We see similar underwater ruins in India's Gulf of Kambat, where sonar scans revealed rectangular formations and stone blocks deep beneath the waves. In the Mediterranean, submerged structures off the coast of Malta bear an uncanny resemblance to the island's megalithic temples, but they lie 60 feet underwater. Off Cuba's western coast, sonar has mapped symmetrical structures half a mile down in a location that would have been dry land more than 10,000 years ago. If Yonaguni is artificial, then it may be part of a global pattern, evidence that large-scale stone architecture existed before the so-called birth of civilization in Mesopotamia. That would require rewriting not just a chapter, but the opening chapter of human history. Skeptics counter with the argument that pareidolia, our brain's tendency to see patterns in random shapes, is tricking us. They point to other coastal rock formations that have straight edges or steps without human intervention. They argue that ocean currents, storms, and the brittleness of sandstone could naturally create Yonaguni's appearance over thousands of years. But if nature alone is responsible, it has an unnerving habit of mimicking human design down to the smallest detail. At Yonaguni, for example, there's a large, upright stone slab that resembles a standing monolith. Its placement is not random, it faces a particular direction, as if marking an entrance. Another section of the site contains a series of parallel grooves, evenly spaced, as though carved intentionally. The deeper you look, the harder it is to wave away the anomalies. Some of the so-called steps at Yonaguni are far too uniform to be explained by the chaotic forces of erosion. And the platform heights often match ratios we find in sacred architecture, where dimensions are tied to astronomy or mathematics. This is not something we expect from natural rock fracture. There's also the curious case of a nearby Yonaguni stone tablet on dry land that bears petroglyphs. Some researchers believe this hints at a connection between the submerged site and ancient cultures that once inhabited the region. If the underwater city was once above sea level, its builders could have been the same people responsible for these carvings, a direct cultural link across thousands of years. The when is almost as provocative as the how. If Yonaguni sank due to post-Ice Age sea level rise, then its construction predates every officially recognized civilization by millennia. That pushes the origins of complex architecture, and perhaps organized society, into the deep prehistoric past. And if the builders of Yonaguni were part of a wider network of coastal settlements, then the rising seas would have erased a vast chapter of human activity. Entire cities, trade routes, and cultural innovations could now be hidden on continental shelves around the world, accessible only to deep-sea exploration. This isn't just speculative archaeology. It's also a sobering reminder of how fragile civilizations are. One shift in climate, one geologic upheaval, and everything can be lost. And if it happened once, it could happen again. So Yonaguni sits there, a riddle in stone beneath the sea. Was it the product of an ancient people whose knowledge and history were swallowed by the ocean? Or is it a quirk of geology coincidentally shaped into something our pattern-seeking minds interpret as man-made? The ocean won't give up its secrets easily. Currents erode the site year after year, blurring edges, softening angles, erasing evidence. The clock is ticking on how much we can still learn from it before it's gone entirely. But Yonaguni isn't the only anomaly that forces us to rethink the human timeline. If we journey west, across the open ocean to the Andes, we'll find a site that stands in the thin air of Bolivia's high plains, a site whose stones fit together so perfectly that not even a razor blade can slip between them. And some of those stones are so massive, even modern cranes would struggle to move them. The deeper we go into this mystery, the more it feels like pieces of a puzzle scattered across continents, and we're just starting to find the corners. Imagine holding a blade that, under an electron microscope, reveals a lattice of alternating layers, iron and carbon so perfectly arranged at the nanometer scale that even today's high-tech metallurgists would struggle to replicate it without advanced laboratory equipment. Yet such a blade exists, not as a product of 21st century precision engineering, but as a relic of the Middle Ages, the famed Damascus steel. Its legend is almost mythic. Warriors spoke of swords that could slice through lesser blades, pierce armor, and remain razor-sharp after countless battles. The origin of such strength was not in the brute force of forging alone, but in something far more elusive, the microstructure. Within these ancient blades, carbon nanotubes and cementite nanowires, phenomena typically born in controlled modern environments, were somehow coaxed into existence by smiths who had never heard of an electron, much less atomic arrangement. Modern experiments have tried to reproduce Damascus steel, and while some have succeeded in creating materials with similar patterns and strength, the precise recipe remains shrouded in mystery. The smiths of the past did not work from written equations. They worked by instinct, tradition, and an almost mystical relationship with their materials. They observed color changes in the metal, listened to the ring of the hammer, smelled the burning charcoal. Sensory cues that, unbeknownst to them, were orchestrating atomic transformations. This is where the atomic precision comes into play. The forging temperature had to be maintained within an incredibly narrow range. Too hot, and the delicate carbon structures would burn away. Too cold, and the metal would refuse to bond at the molecular level. The ratio of ores, the purity of the charcoal, the cooling time after each hammer strike, each variable played a part in arranging atoms into a configuration that modern science would later find extraordinary. But Damascus steel is only one thread in a far older and more intricate tapestry. Across the ocean, in pre-Columbian South America, ancient metallurgists in Colombia's Muisca culture mastered the art of tumbaga, an alloy of gold and copper, with a level of control that defies the crudeness we often associate with early metallurgy. They could manipulate surface composition through a process called depletion gilding, leaching copper from the outer layer to leave a shimmering skin of pure gold. Under magnification, this process reveals a smoothness and uniformity so precise that the difference between atomic layers of gold and copper becomes almost imperceptible. It's easy to dismiss these as happy accidents, a few cultures stumbling upon techniques without understanding the underlying science. But that assumption is convenient only for the modern ego. If these were mere accidents, why do we find such precision repeated across continents and millennia? Why does the same obsessive pursuit of perfect tolerances appear in Japan's samurai swords, India's Wootz steel, the intricate gold filigree of the Etruscans, and the tight interlocking joints of Andean stonework? Consider the case of the Inca walls at Sacsayhuaman. These massive blocks, some weighing over 100 tons, fit together with such flawless precision that not even a razor blade can slip between them. There is no mortar. The blocks interlock with complex shapes, each one carved to fit its neighbors like a three-dimensional jigsaw puzzle. This means the builders were not just shaping one stone at a time, but visualizing and executing a multi-block structure with tolerances measurable in millimeters, and perhaps less. Modern stonemasons, given steel tools and digital modeling software, would still face challenges reproducing such work. The Incas did it with tools made of bronze or stone, and yet the surfaces often show no chisel marks. How was such smoothness achieved? Some researchers speculate they used repeated abrasion with harder stones. Others suggest plant-based acidic compounds that could chemically soften rock, but no theory fully explains the speed, scale, and consistency of their results. This is where the idea of atomic-level thinking becomes more than poetic. Even without knowing the word atom, these ancient craftsmen may have intuitively understood that the behavior of materials changes when manipulated at the smallest scales. Through centuries of trial, error, and intergenerational refinement, they honed methods that altered microstructures, controlled grain boundaries, and directed molecular alignment. And if this sounds improbable, remember that in our own industrial history, many world-changing inventions came before their underlying science was understood. The steam engine predated thermodynamics. Vaccination predated germ theory. Optical lenses were crafted long before anyone knew how light truly behaved. The absence of formal scientific theory does not preclude mastery. There's another dimension here, one rarely discussed in mainstream archaeology, and that is intent. The modern world often prioritizes speed and profit over perfection. Ancient craftsmen, in contrast, often labored for months or even years on a single object. The aim was not efficiency, but transcendence. The artifact was more than a tool or decoration. It was an offering, a statement, a legacy. That mindset changes the calculus of what's worth doing. If you believe your creation will stand for centuries or carry spiritual weight, then aligning a surface to within a hair's breadth becomes not an indulgence, but a necessity. And in many ways, these artisans were closer to the quantum world than we are today. Not in knowledge, but in relationship. They worked with materials in their raw, unrefined states, forging connections between human intention and natural form. The hum of the forge, the smell of stone dust, the tactile feedback of metal under hammer, these sensory experiences were their laboratory instruments. When you hold one of their creations today, a Damascus blade, a gilded pendant, a precisely jointed wall, you are not just holding an object. You are holding a frozen moment where human will and the laws of physics met at a scale invisible to the naked eye. The atoms are still there, arranged just so, locked in a pattern decided centuries ago by hands that never saw them. In the next chapter, we will leave the forge and the quarry behind and step into the realm of measurement itself, because to craft with atomic precision, you must first know how to measure it. And here lies another mystery: the ancient world's astonishing ability to detect and replicate exact dimensions without digital calipers, lasers, or atomic clocks. Imagine a sword forged over 1,000 years ago, its edge capable of slicing through silk with no more effort than a falling feather, its body so strong that it could flex without breaking, and yet so sharp that it could cleave through lesser blades. This was not legend. This was Damascus steel. The name alone carries a weight of myth, conjuring images of master smiths hammering glowing ingots in the flickering light of ancient forges. But the real mystery of Damascus steel lies not just in its legendary performance, but in the microscopic, even atomic, secrets hidden within its very grain. Modern metallurgists, armed with electron microscopes, have uncovered something startling. The steel contains nanostructures, tiny carbon nanotubes, and cementite nanowires woven through its molecular lattice like a hidden code. These features are not something a blacksmith could see, yet they are there, the byproduct of a process that produced perfection centuries before the discovery of the atom itself. How could this be? The production of Damascus steel began with a material called wootz, imported from India and Sri Lanka. Wootz steel was rich in carbon and alloying elements like vanadium. In the hands of skilled Middle Eastern smiths, it was heated and cooled in precise, almost ritualistic cycles. These cycles were not recorded in scientific manuals, but passed down as guarded secrets, like an oral tradition of molecular engineering. Over time, these techniques embedded ordered nanostructures into the steel, arrangements that science would not formally document until the late 20th century. This is where the story becomes unsettling. When researchers at the Technical University of Dresden examined authentic Damascus blades, they found that these nanotubes were not incidental. They were the direct result of repeated thermal cycling that induced the steel to self-assemble at the nanoscale. In other words, ancient smiths, without microscopes, without quantum theory, without even the concept of atoms, had stumbled upon a process that manipulated matter at a level so fine it rivals modern nanotechnology. But here's where the mystery deepens. At some point in history, this knowledge was lost. By the mid-18th century, Damascus steel production had ceased, and the original wootz ingots were no longer available in the trade networks. European metallurgists tried desperately to replicate the steel, but they could not capture its nanostructured heart. The blades they made looked similar, even felt similar. But under the microscope, they were dead copies, lifeless imitations of a living molecular masterpiece. Some argue that this loss was inevitable. The unique ores and carbon sources that produced wootz steel may have been mined to exhaustion, or the precise methods guarded by the last true smiths may have simply vanished when those smiths died. Others, however, see something more deliberate: that such knowledge was never meant to be in the hands of just anyone. After all, to create material that perfectly balances hardness and flexibility is to hold the key to dominance in both warfare and industry. If a society could mass-produce such steel, it could leap centuries ahead of its rivals in technology. And yet, here we are, centuries later, still reverse engineering fragments of those old blades, still marveling at the perfection of their atomic dance. In 2006, a research team in Germany successfully reproduced Damascus-like nanotubes in steel, but only with the aid of modern materials science. Even then, their samples lacked the organic beauty of the originals, the shimmering water-like patterns across the surface that were as much art as function. Those patterns, called watering, were the visible signature of something invisible, the ordered atomic arrays deep within. One has to wonder, if Damascus steel could emerge in a pre-industrial world, what other nanostructures might have been forged in antiquity without our knowing? If a sword could be engineered at the molecular level, could jewelry, armor, or even tools have been similarly constructed? And if so, what else have we overlooked simply because we lack the will to look deeply enough? Consider this. In our time, building carbon nanotubes requires precision instruments, vacuum chambers, and exacting chemical conditions. In the ancient world, it required a hammer, a forge, and an understanding of heat that transcended mere metallurgy, a kind of intuition for matter. Whether this was trial and error refined over centuries or an inheritance from an even older, forgotten civilization is still up for debate. But the fact remains, Damascus steel is an artifact of atomic precision, hiding in plain sight in museums and private collections, a reminder that the line between legend and reality is often drawn in ignorance. When you run your fingers over an authentic Damascus blade, you're not just touching metal, you're touching an achievement that compresses the boundaries of time, culture, and science. You're holding the outcome of a process that whispers of lost laboratories, not the kind with white coats and glassware, but with open flames, stone floors, and the rhythmic ring of hammer on anvil. You're looking at proof that humanity has reached into the fabric of the atomic realm before, perhaps more than once, and then let it slip away. And here's the tantalizing part. In the layering of Damascus, in the invisible threads of carbon nanotubes, there is a strange parallel to quantum entanglement. Separate atoms, bonded in patterns that repeat with uncanny precision, reinforcing each other's properties across scales, micro, nano, atomic. These are principles we now see in cutting-edge materials science, from superconductors to aerospace alloys. It's as if Damascus steel was a message in a bottle, washed ashore from a future we've yet to fully inhabit. The loss of its manufacturing secrets is not just a technological tragedy, it's a philosophical one. It asks us whether human progress is truly linear, or whether we have risen and fallen in cycles, each peak leaving behind cryptic signatures for the next. Damascus steel may just be one of those signatures, a physical reminder that our past may be filled with more advanced moments than we dare admit. And perhaps, if we can decode these ancient atomic footprints, we might recover not just the methods, but the mindset that forged them. Because the real secret of Damascus may not be in its composition, but in its comprehension, the idea that even without modern instruments, we can learn to see with the mind's eye into the smallest building blocks of matter. And if Damascus steel is but one chapter, what else, in the annals of history, might be waiting for us to see not with our eyes, but with our understanding? In the dim light of the laboratory, a single sliver of metal lies beneath the electron microscope. On the surface, it looks unremarkable, just a dull, time-worn fragment of ancient weaponry. But magnified 1,000 times, its story changes. Beneath the lens, there are structures so small, so intricately arranged, that they defy everything we think we know about pre-industrial metallurgy. It is here, at the nanoscale, that the past begins to whisper a different truth. Someone, long before the Industrial Revolution, had mastered the architecture of atoms. One of the most famous examples is Damascus steel, a legendary metal used for swords that were said to cut silk in mid-air or slice cleanly through other blades. For centuries, the secret to its strength and flexibility was lost, reduced to myth and legend. But in the 20th century, metallurgists studying authentic Damascus blades made a startling discovery. Inside the steel were carbon nanotubes, microscopic cylinders of carbon atoms, arranged with a precision that modern nanotechnology only rediscovered in the last few decades. These nanotubes, alongside unique arrangements of cementite, iron carbide, gave the blades their exceptional properties. But here's the puzzle. Carbon nanotubes require specific thermal conditions to form, conditions that ancient blacksmiths could not have known in theoretical terms. They had no electron microscopes, no concept of molecular lattices, and yet they had mastered a forging process that produced results identical to some of the most advanced materials science in existence today. Was this purely the result of trial and error passed through generations? Or was there something more? A legacy of knowledge from an earlier forgotten chapter of human history. Damascus steel is not alone. Consider Wootz steel, originating from ancient India, which became the basis for Damascus itself. Produced in crucibles and traded across the known world as early as 300 BCE, Wootz was famed for its almost magical durability. The ingot's internal microstructures displayed patterns that modern metallurgists recognize as self-assembled at the microscopic scale. Once again, a blend of artisanal instinct and hidden science created a material whose properties could rival, or surpass, our own industrial steel until the mid-20th century. Even older still is the mystery of meteoric iron, metal forged not from Earth's crust, but from the cores of ancient fallen asteroids. Tutankhamun's dagger, analyzed in 2016, was found to be made of such extraterrestrial iron, alloyed with nickel and cobalt in ways that Earth's own ores could not produce. This was not simply a case of melting and casting. The dagger's flawless, corrosion-resistant finish suggests an understanding of alloying and polishing techniques far beyond what archaeologists believed existed in the Egyptian Bronze Age. The deeper we look, the stranger it gets. Roman concrete, for example, is often celebrated for its durability, but far less discussed is the molecular chemistry behind it. Modern concrete crumbles in decades. Roman harbor walls have stood for over 2,000 years in constant contact with seawater. When analyzed at the microscopic level, the lime in Roman concrete was found to be intentionally hot mixed, producing particles that continued to react with seawater over time, healing cracks and strengthening the structure. It's a form of self-repairing material, a concept that modern engineers are only beginning to perfect with synthetic polymers and smart composites. In all these cases, what we see is not merely clever craftsmanship, but craftsmanship that operates at the threshold of atomic behavior, the same threshold that underpins nanotechnology, quantum mechanics, and the materials science of the 21st century. It forces us to confront a provocative question. If these techniques were achieved through pure empirical knowledge, why were they lost for centuries? Why didn't the Industrial Revolution happen in 500 BCE when the building blocks, literally, were already in human hands? Some historians will argue that these were lucky accidents, born from countless iterations of trial and error, with the knowledge locked in oral tradition. Yet, the remarkable consistency in results, whether in India's Wootz steel, the Levant's Damascus blades, or Rome's unyielding sea walls, suggests something more systematic. In metallurgy, minor deviations in process can produce catastrophic failures. To replicate such feats across centuries and continents, without modern instruments, implies either an almost supernatural level of inherited craftsmanship, or written and guarded knowledge far more precise than what has survived. And here is where the speculative door creaks open. Could these be remnants of an earlier scientific understanding, one that spoke the language of atoms long before Dalton formalized the concept in 1803? If so, what happened to that knowledge? Was it lost in the fires of war, swallowed by societal collapse, or deliberately hidden. The most unsettling possibility is that we have not yet recognized the full extent of these achievements because we have not yet looked closely enough. For every Damascus sword we study under a microscope, there may be 100 other artifacts sitting in museums or buried in the ground whose secrets remain invisible to the naked eye. The paradox is hard to ignore. Modern science prides itself on building toward an ever clearer view of reality. But here are ancient works that suggest we are rediscovering truths that someone, somewhere, had already glimpsed. And if they had mastered atomic-level craftsmanship, what else might they have known? In the coming sections, we'll move beyond the forge and into the quarries, where stone, seemingly the most inert and unyielding of materials, bears evidence of shaping and finishing techniques that at microscopic resolution rival the smoothness of machined metal. The mystery deepens, for stone is not just a harder medium, it is a silent witness to technologies that leave no tool marks, no chisel strokes, and no easy explanations. And if the metals could speak, perhaps they would say, "We were not the first to master the smallest scales. We were simply the last to forget." The deeper we dig into the physical remains of ancient civilizations, the more the lines between history and science fiction blur. In the last chapter, we stood in awe at the sheer impossibility of the Serapeum's granite sarcophagi and the megalithic feats of sites like Pumapunku. But now, we must look beyond the stones themselves, to the underlying sciences that might have made such precision possible. Because there's a chance, however small, that we are staring at the fingerprints of forgotten sciences that operated on a scale most people alive today never think about: the atomic scale. Imagine for a moment a workshop in 2500 BC, but instead of bronze chisels and pounding mallets, its craftsmen wield tools that somehow manipulate matter with exactness down to the thickness of a human hair, or even smaller. This isn't just about accuracy, it's about control. Control over how atoms arrange themselves, how crystal lattices grow, and how metallic grains align for maximum strength. We assume that such mastery belongs to the realm of clean rooms, electron microscopes, and nanofabrication facilities. Yet some ancient artifacts behave as if they were shaped by techniques that wouldn't be invented for another 4,000 years. Take the fabled Damascus steel. At first glance, it's simply a form of sword-making, renowned for its beauty and strength. But studies under modern electron microscopes have revealed something startling. Embedded within the steel's structure are carbon nanotubes, microscopic cylinders of carbon atoms arranged with mathematical perfection. We, in the 21st century, use these structures in experimental materials to achieve incredible strength-to-weight ratios. But here they are, locked inside swords forged before the Industrial Revolution. Were they accidental byproducts of an artisan's intuition, or did ancient smiths, through generations of experimentation, discover ways to manipulate materials on a microscopic level, without ever knowing the word nanotechnology? Then there's the Lydian electrum coinage from around 600 BC, some of the earliest coins in history. Analyses have shown a purity and consistency in the gold-silver alloy that would be difficult to achieve without a deep understanding of metallurgy. Modern metallurgists note that the uniform distribution of metals hints at controlled heating and cooling cycles that prevent segregation at the microstructural level, a principle central to today's high-tech manufacturing. In a laboratory, when we manipulate matter with atomic precision, we often rely on machines to do the work for us. Computer-controlled lathes cut to micron tolerances. Focused ion beams etch patterns thinner than a strand of DNA. But an ancient mason cutting basalt with uncanny smoothness had none of this, at least none that we've found. And yet, the result, when measured, sometimes falls within tolerances comparable to our most advanced tooling. One controversial hypothesis proposes that some civilizations may have exploited properties of sound, vibration, and heat to affect matter in ways we don't fully understand. This isn't pure speculation. Modern science knows that ultrasound can cause microscopic cavitation in liquids, that certain frequencies can align crystal grains, and that thermal cycling can create uniform molecular arrangements. Could ancient workshops have been filled with instruments that looked primitive to our eyes, yet produced subtle effects on the materials they worked? There's also the curious matter of lost recipes. Formulas that worked so perfectly that, once forgotten, have proven almost impossible to replicate. Roman concrete is a prime example. Structures made from it have withstood 2,000 years of weathering, storms, and even seawater. Its durability comes from a self-healing property at the microscopic level, lime crystals that slowly grow over time to seal cracks. Modern engineers have reverse-engineered this process, but the fact remains, ancient builders were creating materials with behaviors we only recently learned to explain scientifically. And then there are the oddities that resist any neat explanation. Microscopic gold spheres found embedded in quartz from South Africa, dated, if the geological context is correct, to billions of years before humans walked the earth. The Baghdad battery, a clay jar with components that could produce a small electrical charge. The precise drilling marks in Egyptian stone that suggest a tool feed rate and pressure inconsistent with hand-powered methods. None of these alone prove atomic-scale craftsmanship, but together they hint at a broader, stranger picture. If such techniques existed, why were they lost? Perhaps because they weren't widely understood even then. It's one thing for a small cadre of master artisans to guard a process like a sacred secret. It's another for that knowledge to survive the collapse of an entire civilization. Technologies, especially those that depend on delicate, repeatable processes, can vanish overnight if the chain of apprenticeship is broken. A sudden war, a plague, the death of key masters, and the craft becomes legend. Yet some of these techniques seem so far beyond their time that the word legend feels insufficient. When modern scientists find nanostructures in an ancient blade, they recognize the physics immediately, but are left wondering whether they're seeing a happy accident or a deliberate feat. And if deliberate, how much more might have been possible in those lost workshops? Could there have been ancient counterparts to our semiconductor fabs, not in clean rooms but in stone halls with techniques we have yet to decode? We also have to consider the uncomfortable possibility that our timeline of technological development is wrong, or at least incomplete. If civilizations capable of working with such precision existed far earlier than we think, then their works might be buried deep below layers of earth and history, their tools reduced to dust. What survives are the toughest artifacts, the stones, the metals, leaving us to reverse engineer their genius with only fragments in hand. Standing in a museum today, you might look at a polished obsidian mirror from Mesoamerica or a flawlessly cut crystal lens from ancient Egypt and feel the faintest echo of this mystery. The knowledge is gone, but the proof remains in the perfection of the work. And in that perfection lies a challenge, perhaps even an invitation, for us to rediscover not just the how, but the why behind these feats. Because if ancient engineers could shape matter with such mastery, they weren't just building tools, weapons, or monuments. They were sending a message, across centuries, across millennia, that skill and understanding can transcend the limits of time. The question is whether we're ready to hear it, and whether in seeking their secrets we might uncover something far greater than precision itself. Imagine holding a sword whose blade seems to shimmer with the flow of water, yet beneath that beauty lies a structure so advanced that modern scientists, peering through electron microscopes, have found arrangements of carbon atoms and iron on a scale so precise it borders on nanotechnology. This is Damascus steel, a material whose name has become a byword for both mystery and mastery. Forged in the crucible of ancient knowledge, it carried secrets that even the most skilled modern metallurgists struggled to reproduce for centuries. But here's the deeper question. Did its creators truly understand the microscopic marvels they were crafting, or was their genius born of painstaking tradition, passed down through generations until the exact process faded into legend? The story begins in the ancient Near East, possibly as far back as 300 BCE, though it would truly capture the imagination of the world between the 9th and 18th centuries. The blades of Damascus, feared by crusaders, coveted by kings, were made not just to cut, but to endure. They could slice through lesser weapons, hold an edge after countless battles, and resist breaking under stresses that would shatter ordinary steel. What gave them this strength was not magic, though it may have seemed that way, but a complex dance of chemistry, heat, and time. The core ingredient was Wootz steel, originating in India and Sri Lanka, a high-carbon alloy produced in small, sealed crucibles. This was no accident. The sealed environment prevented the loss of carbon during smelting, allowing the molten metal to cool into ingots that had a distinct microstructure. These ingots were then exported along trade routes to the blacksmiths of Syria, Persia, and beyond. There, the transformation into Damascus steel began, a process involving precise temperature control, repeated heating and forging, and a mastery of timing that would determine the alignment of carbon nanotubes and carbide structures within the blade. Here's where the atomic scale intrigue comes in. Modern metallurgical analysis has shown that true Damascus blades contain carbon nanotubes and nanoscale sheets of cementite, arrangements of atoms that form patterns repeating over distances of mere billionths of a meter. These structures are not just aesthetically pleasing. They give the blade its remarkable combination of hardness and flexibility. To achieve this in a pre-industrial world is astonishing, akin to building a cathedral with stones carved to molecular tolerances without ever seeing the molecules themselves. And yet this perfection was fragile in another sense. The process was deeply dependent on the unique chemical makeup of the original Wootz ingots. As trade routes shifted and the original ore sources ran dry, the exact carbon and trace element ratios changed. By the 18th century, blacksmiths found that their blades, while still beautiful, no longer possessed the legendary properties. The art, once thriving, began to fade into myth. But the allure of Damascus steel never faded entirely. In the 20th century, metallurgists tried to reverse engineer the process, scouring historical records, experimenting with crucible smelting, and analyzing surviving artifacts at the atomic level. They succeeded to a degree. Modern reproductions can match many of the mechanical properties and even mimic the surface patterns. Yet questions remain. Did ancient smiths, through trial and error, arrive at methods that effectively manipulated matter on the nanoscale without ever knowing such a scale existed? Or was the atomic precision an unintended consequence of larger, more visible craft decisions? The choice of ore, the rhythm of the forge, the cooling cycles whispered from master to apprentice. There's another wrinkle to the story. Some researchers have proposed that the techniques used to produce Damascus steel may have originated from even older metallurgical traditions, knowledge passed down from Hellenistic or even earlier civilizations, adapted and refined over centuries. If true, then Damascus may not be a singular invention, but rather the pinnacle of a continuous thread of atomic-level craftsmanship stretching back into deep antiquity. This aligns with the broader mystery at the heart of our investigation. How many of the so-called miracles of ancient engineering were the result of unbroken lines of practical empirical science, now fractured and lost? When we compare Damascus steel to other ancient materials, the parallels become striking. Roman concrete, which can self-heal after centuries in seawater. The nanostructures in stained glass windows from medieval cathedrals, created by accident through metallic nanoparticles suspended in glass. The fused surfaces of ancient South American stonework, suggesting heat or pressure techniques unknown today. In each case, we see a pattern. The apparent leap into atomic or molecular mastery, achieved without a microscope, and often without a formal scientific theory to describe it. Damascus steel, then, is more than just a chapter in the history of metallurgy. It is a symbol of the gap between knowing that something works and knowing why it works. It is also a reminder that the boundary between science and craftsmanship is not always clear. To create a blade with the strength of Damascus, one needed not only the physical skill to work the metal, but also an intuitive grasp of heat timing and material behavior, a kind of embodied science where the data lived in muscle memory rather than in books. And perhaps this is why the loss of Damascus steel still stings. We did not merely lose a manufacturing process, we lost a way of thinking, a way of engaging with materials that treated them not as inert substances, but as living participants in the forge. That relationship, honed over centuries, could produce results that modern industry, for all its precision, still regards with awe. In our journey through ancient machines built with atomic precision, Damascus steel stands as both a triumph and a tragedy. A triumph because it proves that human beings, without electron microscopes or computer modeling, could still shape matter at the smallest scales into tools of unmatched performance. A tragedy because the knowledge slipped away, not into deliberate secrecy, but into the slow erosion of trade, resources, and tradition. Yet the mystery endures. Each surviving blade, lying in a museum or hidden in a private collection, is a silent challenge to our understanding. If they could do this then, what else might they have achieved? What other atomic arts might be waiting to be rediscovered, or perhaps reinvented, in our own age? And this brings us to our next enigma, one that blurs the line between metallurgy and architecture. If Damascus steel shows atomic precision in a weapon, what happens when that same mastery is scaled up, shaping not a blade but an entire monument? If there is one artifact that encapsulates the mystery of ancient atomic-level mastery, it is Damascus steel. For centuries, these blades were whispered about with awe, feared on battlefields, and revered in royal courts. They were said to cut through lesser swords like cloth, to shear hair drifting in the air, even to slice a silk scarf without fraying a thread. And their distinctive surface, an intricate flowing pattern that looked almost alive, hinted at something far beyond mere metallurgy. This was not just a weapon, it was a statement, mastery over matter itself. Our story begins not in Damascus, but somewhere in the crucible of trade between India, Persia, and the Levant. Historical evidence suggests that the fabled steel was forged from Wootz ingots imported from southern India, a material prized for its purity and unique carbon content. These ingots, already an achievement of controlled smelting, were then transformed in Damascus and other centers into blades that became the gold standard of edged weapons. But it was how they did it that remains the enduring mystery. When modern scientists finally got their hands on genuine centuries-old Damascus blades, they expected to find simple high-carbon steel. What they found instead stunned them. Nanoscale carbon tubes and cementite nanowires, structures so fine and precise they could only be seen under powerful electron microscopes. These are materials we associate today with advanced nanotechnology, not with forges blazing in medieval markets. How could smiths from the 10th century possibly have manipulated matter at a scale of billionths of a meter? One theory is that they never consciously saw what they were creating, at least not in the modern sense. Instead, through generations of empirical experimentation, trial and error, and a deep understanding of the behavior of metals under heat and hammer, they developed a process that produced these nanostructures naturally. The blend of iron, trace elements like vanadium and tungsten from the ores, and an almost ritualistic heating and cooling cycle could have aligned the carbon atoms into these nano-configurations. Their senses were their instruments, and time was their laboratory. But there's a counter-theory, one that brushes against the fringes of conventional history. Some researchers argue that the Smiths were guided by knowledge that was not the result of simple trial and error, knowledge passed down from an earlier civilization, now lost to time. The precision required to achieve uniform nanowire distribution in steel is so extreme that even modern metallurgists struggle to replicate it consistently. If the medieval smiths had stumbled onto it by chance, Why was the method eventually lost? Why didn't the skill spread, evolve, and dominate metallurgy worldwide? Part of the answer lies in the fragility of tacit knowledge. The process was not written in engineering manuals, but carried in the memories and muscles of master smiths. When those lines of apprenticeship broke, perhaps due to war, political upheaval, or the disruption of trade routes, the secrets vanished. By the late 18th century, the art of true Damascus steel was gone, replaced by inferior imitations. What we have today, labeled Damascus in shops and markets, is decorative pattern-welded steel, aesthetic cousins to the original, but without its otherworldly properties. Yet even with the loss, the legacy of Damascus steel forces us to confront uncomfortable questions about human history. Could ancient and medieval craftsmen have had access to principles of atomic and molecular structuring that we've only recently rediscovered? Was the magic of Damascus merely an accident of materials and process, or was it the echo of a more sophisticated technological tradition, one whose origins stretch back further than we dare admit? Consider this. In the realm of modern materials science, nanostructures are not trivial curiosities. They are the foundation of advanced electronics, high-performance composites, and cutting-edge medical tools. They require clean room laboratories, computer modeling, and industrial precision. Yet, Damascus blades, made in smoky forges with bellows and anvil, were achieving something similar over 1,000 years ago. And perhaps the most compelling aspect of the Damascus mystery is its intersection of beauty and function. The swirling patterns on the blade, often described as watered or flowing, were not merely decorative. They were the visible fingerprints of the underlying atomic arrangement. Each ripple in the steel surface told a story of molecular alignment, of heat cycles timed to perfection, of carbon atoms dancing into place. Today, metallurgists attempting to recreate Damascus steel often find themselves teetering between frustration and awe. Some have come close, reproducing blades with similar nanostructures, but the exact combination of ore impurities, forging technique, and cooling rates that birthed the original remains elusive. It's as though the steel itself resists full rediscovery, guarding its secrets as fiercely as the warriors who once wielded it. The question that hangs in the air is this: if Damascus steel is a remnant of ancient atomic precision, what else might have been possible for those who mastered such craft? Could they have applied similar techniques to tools, armor, or architectural elements? Were these nanostructures just one facet of a broader, forgotten science? Or was Damascus steel an isolated peak, a singular triumph born of the perfect marriage between nature's resources and human ingenuity? As we move forward, we will step away from the forge and into the quarries, where stone rather than steel bears the marks of impossible precision. But remember this: Damascus steel is proof that even without microscopes, even without the language of nanometers, our ancestors may have manipulated the building blocks of matter itself. And if they could achieve that with fire, hammer, and the wisdom of generations, what limits were there, really? If the ancients did wield atomic-level precision, why did it vanish? This question gnaws at the edges of our curiosity, like an unanswered chord that refuses to resolve. Throughout history, the march of technology has often been a cumulative ascent. We build upon the discoveries of those who came before. Yet here, in the cold stone and aged alloys of the past, there is a strange inversion. Peaks of craftsmanship rising from an otherwise primitive technological landscape, never to be reached again until modern times. It's as if the path to progress was interrupted, or deliberately rerouted. The paradox is best illustrated by the Great Pyramid's alignment, so exact to true north that modern engineers struggle to replicate it without laser guidance. This is juxtaposed with the fact that, according to mainstream archaeology, the tools available were copper chisels and simple rope plumb lines. There's a jarring mismatch between means and result. Were these truly the only tools, or have we lost the knowledge of a parallel toolkit one that didn't survive in the archaeological record because it wasn't made of stone or metal. Ancient precision often presents itself in ways that seem oddly selective. A culture might produce one or two pieces of astonishing craftsmanship, surrounded by works of visibly lesser quality. It's as if a momentary brilliance flared, a master artisan or small circle of technologists guarding their methods, only for those methods to vanish when they died or the society collapsed. The Antikythera mechanism is the quintessential example, a mechanical computer capable of predicting astronomical events with uncanny accuracy. It appears once in the record, then not again for over 1,000 years. Some argue that this isn't a mystery at all, merely the randomness of preservation, that countless other examples of high-precision work existed but were destroyed by time, climate, and human interference. But this explanation struggles against the weight of certain anomalies, not just in stonework, but in metallurgy, ceramics, and even textiles, that defy both the chronological context and the available manufacturing processes we currently attribute to their era. One possibility is that ancient cultures possessed a form of soft technology, processes, techniques, or instruments that relied less on physical machinery and more on knowledge systems and methods that left no durable trace. Think of modern semiconductor manufacturing. Without the clean rooms, vacuum pumps, and photolithography masks, the process is nothing but an idea. If an entire global collapse occurred tomorrow, the physical remnants of our most advanced production systems would degrade rapidly, leaving little evidence for future archaeologists to deduce our true capabilities. Another hypothesis turns toward the realm of trade secrets and monopolies. Perhaps there were ancient guilds, not unlike medieval craft guilds, whose value lay in guarding proprietary knowledge, passing it down orally or through tightly controlled apprenticeships. If those guilds perished in war, famine, or political upheaval, their guarded techniques could vanish almost instantly. In this light, ancient precision may have been less about a globally shared skill set and more about isolated pockets of mastery. Yet there is a more unsettling possibility that some of this lost precision was the byproduct of forces or tools we no longer possess, and that its disappearance was not accidental. Imagine a technology so potent, so far ahead of its time, that those in power deemed it too dangerous to leave in circulation. Whether through fear of misuse, religious decree, or societal upheaval, such knowledge could have been deliberately suppressed. The burning of the Library of Alexandria is often invoked here, though historians debate its true scale. Still, it serves as a symbol for how fragile knowledge can be and how swiftly it can vanish from the human record. Modern reverse engineering efforts reveal just how alien some ancient work is when subjected to microscopic analysis. The lattice structures in Damascus steel, for instance, were only understood in the last few decades, patterns of carbon nanotubes embedded in iron that give it both strength and flexibility. These weren't crafted intentionally at the nanoscale by medieval blacksmiths, at least as far as we know. And yet the results were consistent enough to suggest a deliberate, if unspoken, mastery of conditions and materials that today we'd recognize as nano-engineering. The same can be said of certain Incan stone walls whose interlocking blocks fit so tightly that not even a razor blade can slide between them, despite being assembled without mortar. Some researchers suspect thermal or chemical treatments, perhaps plant-based acids or unknown binders, could have allowed the surfaces to be softened or fused at the micro level before setting into their final rock-solid form. If true, these would represent a form of material science that was not only advanced but deeply practical and yet somehow entirely forgotten. In grappling with this paradox, we are forced to confront uncomfortable truths about our own era. We assume progress is linear and cumulative, but history whispers a different tale, one of rises and collapses, of knowledge gained and then scattered to the wind. The idea that we might be living in another such peak, vulnerable to the same fate, is sobering. The devices in our pockets, the satellites in orbit, the quantum computers in laboratories, All of it could become opaque mystery to a future civilization if the chain of knowledge were broken. The paradox of lost precision, then, is more than an archaeological curiosity. It's a mirror held up to the fragility of civilization itself. Each impossibly perfect cut, each inexplicable tolerance preserved in stone or metal is both a marvel and a warning. They whisper of what can be achieved and how easily it can be erased. And as we stand on the cutting edge of our own technological era, perhaps the most important lesson isn't how the ancients did it, but how we ensure that our own hard-won precision, atomic or otherwise, survives the tides of time. Because if history has taught us anything, it's that perfection is fleeting, and the memory of how to achieve it even more so. The deeper archaeologists peer into the microscopic and atomic details of ancient artifacts, the more the narrative fractures between two seemingly irreconcilable camps. Those who attribute these impossibly precise creations to the ingenuity of human craftsmanship within known historical timelines, and those who believe they hint at lost epochs of technological brilliance now reduced to scattered ruins and enigmatic relics. By now, the evidence feels like a mosaic with more missing tiles than complete images, tantalizing glimpses of an unspoken chapter of human history. At first glance, the sculptures of ancient Egypt, the tight-fitted masonry of the Andes, or the flawlessly drilled stone beads of the Indus Valley could be explained as mere mastery of hand tools, perhaps aided by simple but clever innovations. But magnify their surfaces to the level of microns or nanometers, and the story changes. Suddenly, a seam in granite becomes a perfectly planar interface. A polished obsidian mirror reveals a surface so smooth that by today's standards, it rivals semiconductor wafers. What's striking is not just the level of craftsmanship, it's the statistical improbability of it occurring over and over again in cultures separated by oceans, languages, and millennia. This is the point where some researchers begin to quietly speculate. Were these skills independently discovered multiple times in human history, or were they inherited fragments from an older global knowledge system? The human timeline, as conventional archaeology presents it, places the rise of complex civilization somewhere around 6,000 years ago, with the rapid acceleration of technological advancement in the past few centuries. But there's a growing body of physical evidence that challenges this neat, linear trajectory. Take the mysterious Iron Pillar of Delhi, standing for more than 1,600 years without significant corrosion, its surface containing an unusual passive protective film that even modern metallurgists still debate. Or the finely inlaid jewelry from Ur, whose gold-to-silver ratios and micro-soldering techniques suggest a metallurgical sophistication we don't typically associate with the Bronze Age. One of the most compelling threads in this investigation comes from the realm of ancient metallurgy at atomic resolution. Damascus steel, famed for its legendary strength and wavy patterns, is known today to contain carbon nanotubes, hollow cylindrical carbon molecules with extraordinary tensile strength embedded in the steel matrix. These nanotubes are a staple of modern nanotechnology, yet metallurgists analyzing 17th century blades found them formed naturally during the forging process. Whether this was an accidental byproduct or an intentional, repeatable technique remains one of the great unanswered questions. If the latter, it implies that blacksmiths in the Middle East were manipulating atomic-scale structures centuries before scanning electron microscopes even existed. Some scholars suggest that artisans observed macroscopic effects, such as the blade's unmatched sharpness or resilience, and refined their methods generation after generation until they could reliably produce these results. The process itself may have been a highly guarded secret, its true understanding lost when the last master smiths died. But this still leaves a question hanging in the air. Was this merely intuition honed over centuries, or the vestige of an even older body of material science? Similarly, in South America, some of the most puzzling metallurgical finds involve the mysterious tumbaga alloy, a blend of gold and copper often used for ceremonial objects. In certain cases, the alloying and depletion gilding processes appear to have achieved atomic-scale uniformity, something that even today requires controlled environments and precise thermal management. How these artisans achieved such control, without access to modern kilns or temperature gauges, remains a mystery that quietly unsettles the tidy boundaries of our historical models. Critics of the lost technology hypothesis point out that extraordinary skill can emerge under the right social and cultural pressures. Civilizations with elite patronage, long apprenticeship systems, and a steady supply of skilled labor could achieve feats that seem miraculous to outsiders. The Egyptian stonemason shaping a diorite vase by hand was not an amateur hobbyist. He may have spent decades refining his technique under the watch of master artisans. Similarly, the Incan architect overseeing the fitting of Cyclopean stones may have commanded hundreds of workers in a coordinated, precision-driven workflow where mistakes were unacceptable and materials were abundant. And yet, the anomalies stack higher. The more one studies the most extreme examples, the more the statistical likelihood of them all being the product of chance and skill alone begins to thin. There's a tipping point where pattern recognition whispers in the background. This is not just about scattered outliers. It's about systemic mastery across multiple domains, times, and places. This is where the concept of technological punctuations enters the conversation, the idea that human history may not be a slow upward slope, but a series of spikes in technological capability, followed by declines and amnesia. In this model, civilizations may reach sudden peaks of innovation, driven by environmental, social, or even outside factors, and then collapse before the knowledge can be widely preserved. The material remnants left behind for future generations are like breadcrumbs from an unknowable banquet. To be clear, these spikes wouldn't necessarily require extraterrestrial intervention or mythical Atlanteans. They could simply be the result of uniquely favorable combinations of resources, cultural priorities, and gifted minds that converge for a few generations before vanishing again. But the magnitude of precision we are discussing, down to atomic-scale craftsmanship, makes the mystery harder to reconcile. The challenge for modern researchers is that most of these relics cannot be reverse-engineered without destroying them. Museums are understandably reluctant to hand over a ceremonial mask or a 2,000-year-old gemstone for metallurgical dissection. As a result, much of the work relies on non-destructive imaging, spectroscopy, and careful surface analysis, leaving the deeper secrets, the ones embedded in the material's very lattice structure, tantalizingly out of reach. This lack of direct access fuels the speculative fire. In its absence, we are left with high-resolution images of nanoscale structures, unexplained consistencies in tolerance and alignment, and the recurring whisper of something older, stranger, and perhaps more advanced than the neat arcs of our history books will allow. And while the academic mainstream remains cautious, the artifacts themselves, silent, immovable, and stubbornly precise, continue to speak across millennia. In the next part, we will step away from metallurgy and turn to an equally baffling frontier: ancient construction techniques that align megaliths and monuments with astronomical bodies at sub-arc-minute precision, alignments so exact that they rival and in some cases surpass modern surveying tools. If the atomic craftsmanship of ancient metallurgy hints at mastery over the smallest building blocks of matter, then these celestial alignments suggest an equally improbable mastery over the vast distances of the heavens. Together, they form a picture that is both exhilarating and deeply unsettling. The deeper we journey into this labyrinth of ancient precision, the more the boundary between possibility and impossibility begins to blur. For centuries, mainstream archaeology has painted a clear arc of human technological evolution, from stone tools to bronze, from iron to steel, from the steam engine to silicon microchips. But when we peer through the lens of artifacts that defy their supposed limitations, we see cracks in that arc. And through those cracks, an unsettling question emerges. What if some of humanity's greatest technological leaps didn't happen in the last 200 years, but were rediscoveries of knowledge once possessed and then lost. Consider the quiet revelations coming from modern material science laboratories. Under electron microscopes, certain ancient alloys reveal crystalline alignment so uniform that even with computer-controlled equipment, producing the same consistency today would be prohibitively expensive. Damascus steel, already celebrated for its legendary sharpness and resilience, has been shown to contain carbon nanotubes, tiny cylindrical structures made of carbon atoms arranged in hexagonal lattices, with properties so extraordinary that NASA has studied them for aerospace applications. These nanotubes are not incidental impurities, they're integrated into the metal in ways that suggest intentional design. Yet we are told this was simply the happy accident of medieval smiths. If so, why do similar nanostructures appear in other cultures separated by oceans and centuries? In certain South American ceremonial blades, in Japanese katanas of the highest grade, even in fragments of ornamental metal recovered from ancient burial sites in Africa. Patterns begin to emerge, patterns of advanced metallurgy that whisper of a shared, deeper understanding. And if such knowledge existed, what else might have been within reach? This is where archaeology edges into uncomfortable territory. There is a reluctance to admit that ancient builders and smiths could have wielded capabilities on par with, or even exceeding, our own in specific domains. The prevailing model prefers to see history as a staircase, each generation building predictably on the last. The existence of anomalies, especially ones that require explanations invoking atomic-scale precision, threatens to turn that staircase into a far messier landscape of peaks and valleys, of lost ages of light and dark. Take, for example, the precise interlocking stones of the Inca walls in Cusco and Sacsayhuaman. We marvel at their tight joins, so tight that even a razor blade cannot pass between them. Some explanations invoke careful chiseling and iterative fitting, but those who've studied the surfaces up close with modern profilometry note that the stone's surfaces aren't just flush. They follow each other's contours with remarkable fidelity over long distances. This kind of precision fitting, even in soft materials, is difficult without measurement tools calibrated to thousandths of an inch. In hard and brittle stones like andesite and diorite, it borders on miraculous. Could the shaping process have involved some method of controlled material removal at the microscopic level, perhaps even thermal or chemical treatments that altered the stone's crystalline structure before final shaping? Ancient Egyptian stonework poses similar mysteries. The famous granite sarcophagus inside the Great Pyramid shows signs of flatness and squareness approaching modern machine shop tolerances. Boreholes in granite and basalt exhibit spiral tool marks, consistent with feed rates far exceeding hand-cranked drills. Modern machinists have compared them to marks left by high-speed, diamond-tipped boring equipment, something that officially didn't exist until the industrial era. If these patterns were isolated, they might be dismissed as coincidences or exaggerations. But when we combine metallurgy, stonework, ceramics, and even ancient optics, the web becomes harder to ignore. In 19th century archaeological digs in Nineveh, Assyrian lenses made of rock crystal were uncovered, some with spherical curvatures accurate enough to magnify images without significant distortion. In the Indus Valley, beads made of carnelian were drilled with holes less than a millimeter wide, perfectly straight and polished smooth. These details aren't just aesthetically pleasing. They imply control at a scale where human vision is insufficient, which means there must have been measuring tools or feedback systems beyond the naked eye. This forces us to confront a paradox. If ancient craftspeople could achieve these feats without digital micrometers, scanning electron microscopes, or computer numerical control machines, then either, 1, they had alternative techniques just as precise but wholly different from ours, or 2, they had access to tools or knowledge that has since vanished without leaving behind its infrastructure. In both cases, the implication is staggering. Because if knowledge can vanish once, it can vanish again. And here is where the mystery takes on a warning. We tend to view our own era's technology as permanent, as the final and inevitable peak of progress. Yet the archaeological record may be telling us that even mastery at the atomic scale is not immune to time's erosion, that civilizations can hold the key to manipulating matter with surgical precision and still lose it. And when they do, the survivors may carry only myths, half-remembered instructions and artifacts whose makers they can no longer emulate. Imagine if tomorrow every microchip factory on Earth was destroyed, not just the buildings, but the expertise to recreate them. Within a single generation, the ability to etch silicon at the nanometer scale would fade from living memory. Within a century, the surviving chips might be seen as magical relics. Within 1,000 years, they could be taken as proof of divine intervention. So, when we encounter an ancient gold pendant with filigree finer than a human hair, or a ceramic glaze fused at molecularly uniform thickness, we must ask, are we looking at the pinnacle of that culture's craft, or are we seeing only what survived, the fragment of a far larger mastery, one that we have yet to match in full? This was the threshold before our final descent into the heart of the mystery. Ahead, we will confront the most controversial possibility of all, that ancient precision wasn't merely the product of lost tools, but the byproduct of an entirely different way of thinking about matter itself, one that might rewrite our understanding of what it means to be a technological civilization. Imagine for a moment that the entire human story is a book, and that we are missing most of its chapters. The pages we hold are worn, incomplete, and bound together with the threadbare strings of surviving records, myths, and ruins. Yet every so often, we stumble upon a detail so sharp, so precise, that it feels as if a sentence from a lost chapter has been etched into the margin, waiting to be deciphered. In the context of ancient machines and atomic precision, these details manifest not just as anomalies, but as echoes, and echoes have a peculiar quality. They carry the shape of the original sound, but with distortions, fading, and interference. The precision artifacts we uncover today may be just such echoes, faded remnants of a technology or knowledge system so far ahead of its time that even when reduced to ruins, they retain measurable perfection. Take, for instance, the curious case of the Lycurgus cup. To the naked eye, this 1,600-year-old Roman glass goblet is a beautiful piece of craftsmanship, adorned with intricate scenes. But under light it changes color, shifting from opaque green to a deep, translucent red. For centuries this was seen as a mere artistic flourish. Only modern microscopy revealed the truth. The glass contains nanoparticles of gold and silver, dispersed at the scale of tens of nanometers. A level of control over material properties that would challenge modern nanofabrication labs. If such a technique arose in isolation, one could argue it was a fluke, a happy accident of mixing impurities. But that explanation grows shaky when we place it alongside other examples. The carbon nanotubes embedded in Damascus steel blades, the crystalline structures in pre-Columbian metalwork, the almost molecular uniformity of certain Mesoamerican obsidian tools. None of these examples were consciously described in atomic terms, and yet the result is indistinguishable from deliberate manipulation of matter at that scale. The natural instinct of modern historians is to frame these feats as accidental discoveries, as if the ancients stumbled upon molecular precision without knowing it. Perhaps. But what if their conceptual framework, though different from ours, was not blind? What if they perceived patterns, symmetries, and transformations at scales they couldn't directly see, yet could still control through ritualized processes, empirical iteration, and encoded traditions? In other words, they may not have needed to know why something worked in order to master how it worked. Consider how long humanity used fire before understanding combustion, or how ancient mariners navigated by stars without knowing stellar distances. Mastery does not always require full theoretical comprehension, only reliable repetition. And in the case of these atomic echoes, the repetition might have been bound to systems of craft, apprenticeship, and perhaps even sacred secrecy. But here lies the tragedy. Precision without preservation is fragile. Once a technique is lost, once the chain of apprenticeship is broken, the method can vanish for centuries or millennia. Without documentation in the language of science, future generations might encounter only the artifact, divorced from the knowledge of its making. That is why the rediscovery of these skills today often comes as a shock. We have no record of the hands, minds, and philosophies that brought them into being. The implications are staggering. If civilizations before us achieved atomic-level craftsmanship, what other sciences might they have touched? Could they have manipulated sound frequencies to alter material structure? Could they have engineered composite materials indistinguishable from nature? Could they have used principles of resonance, magnetism, or pressure in ways we have yet to replicate? It's tempting to dismiss such speculation as the domain of fringe theorists. But remember, only a century ago, the concept of manipulating individual atoms was itself the stuff of science fiction. Today, scanning, tunneling microscopes allow us to arrange them like beads on a string. Our disbelief in ancient atomic knowledge says more about the limits of our imagination than it does about the possibilities of the past. There's also a deeper, almost philosophical dimension here. If the universe is, at its core, a dance of particles and forces, then to shape reality is, in a sense, to learn the steps of that dance. Perhaps ancient engineers didn't discover atomic precision so much as they learned to move in time with the underlying rhythms of matter. Ritual, intuition, and craftsmanship could have been the sheet music by which they composed their creations. Some of the most intriguing possibilities emerge when we think of these echoes not as isolated sparks, but as part of a larger, now lost pattern. The Great Pyramid's alignment, the polygonal masonry of Sacsayhuaman, the finely drilled stone vases of Saqqara, perhaps they were all chapters in a story where understanding structure and resonance at every scale, from the cosmic to the atomic, was the guiding principle. If that's true, then what we're left with are the fragments of a lost symphony, notes scattered across time and continents. And the question becomes, can we, with modern tools and ancient clues, reconstruct the music? The pursuit is not without peril. There's an alluring danger in projecting too much onto the past, in seeing intentionality where none existed. Yet there is an equal danger in underestimating the capacities of those who came before us. To walk between those two extremes requires both skepticism and wonder, the very balance that drives science forward. As we stand on the edge of atomic mastery today, capable of crafting quantum dots, manipulating DNA, and building materials atom by atom, we may find ourselves, centuries from now, in the same position as those ancient artisans. What knowledge will survive us? Which techniques will be rediscovered and cause future generations to ask, how did they do this? It is here, at this intersection of humility and ambition, that we glimpse the true weight of these echoes. They are not just reminders of what has been lost, but challenges, gauntlets thrown across the centuries, daring us to pick them up. And so the question remains, when we finally hold those lost notes in our hands, will we merely marvel at their beauty, or will we learn to play the symphony again? The more we peel back the layers of time, the more it becomes clear that history is not a straight line of progress. It is a jagged path, peaks of brilliance, valleys of loss, where civilizations have risen to dizzying heights of innovation only for their secrets to vanish into the dust. The megaliths, the metals, the alignments, each is a whisper from a past that refuses to be silent. And in those whispers lies the uncomfortable truth. Our ancestors may have mastered methods we cannot yet replicate, let alone fully understand. Think of the way we speak about the information age as though it is unique. But what if there were precision ages long before us, eras in which the tools of creation reached scales so fine they danced on the edge of the atomic? To us, This sounds like science fiction, yet in the rusted grains of Damascus steel, in the polished faces of granite blocks, in the fused seams of artifacts thousands of years old, the evidence stubbornly lingers. If it is not proof, it is at least a challenge to admit that perhaps we have not discovered everything worth knowing. There's an irony in the fact that our own technologies, electron microscopes, high-resolution spectroscopy, 3D scanning, have made us aware of this hidden precision. Without them, we would have seen only old rocks and rusted blades. But now, those same tools reveal stories our textbooks have yet to catch up with. Stories that rewrite the boundaries between myth and engineering. And so we are left with two possibilities. One, these anomalies are the rare accidents of chance, the byproducts of trial, error, and remarkable luck. Or two, they are the deliberate results of lost knowledge, techniques once so common they were mundane, until the hands that knew them were gone forever. But perhaps there is a third possibility, that this is not just about the past. It is a reminder for the future. Civilizations fall, knowledge fades, skills vanish when they are no longer valued. The question is not whether we can rediscover what they knew, but whether we will protect our own innovations well enough to ensure they survive us. In the end, the mystery of ancient atomic precision is not just a riddle for archaeologists, it's a mirror in which we see both the heights of human ingenuity and the fragility of the thread that connects us to it. And maybe, just maybe, it's also a warning. Thank you for joining us on this extraordinary journey through the cosmos here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.